Hi there, this is Sam, a chemical engineer with a passion for solving complex problems and sharing what I learn along the way. On this channel, I break down real engineering challenges, from CFD simulations to chemical processes, into simple, step-by-step solutions you can actually use. Whether you're a student, a researcher, or an engineer in the field, you'll find practical, applicable content here. And if you're looking for extra resources, downloads, or detailed explanations, everything I cover is linked on my blog, blog.sam.musavi.com, where you can dive deeper anytime. If you find this content helpful, give the video a thumbs up, leave a comment, I read them all, and don't forget to subscribe to the channel so you never miss an update. Let's keep learning and building the smartest solutions together. Thanks for being here once again, and welcome to the channel.
Hello and welcome back. And this is a relatively short course about the introduction of OpenFoam 12 programming. We are going to introduce all can do in the OpenFoam with 3 examples. The first one, we will take a look into a scaled viscosity power law. And in the second episode, we will go to the custom boundary condition, and then we define a scalar transport equation in the third session. Before we jump into the topic, I should mention a number of points. This is a 3-session course, which I already mentioned about the topic of each episode. The second point is that you can ask your questions into the comment box, and also drop me a comment if you have your own idea and we can explore it together. And if you have some more ideas about expanding this 3-session course, we can take a look into it together and learn new things with our companionship. Another point is that to follow this course, you should already be familiar with the OpenFoam and its structure. Specifically, we are going to program inside the OpenFoam 12 environment, so it's necessary to be familiar with the OpenFoam version 12 itself. Also, you need a C++ knowledge, at least from beginning to intermediate level. Of course, we try to cover it to some extent here in this session, but because of the time, if you need much more from C++ in your own custom library, you should take a look to the course with C++. But right now, for the following 3 sessions, I will tell you enough about the C++, and it will cover your needs about the programming parts you will face in these 3 sessions. As I said, the programming will be on the OpenFoam 12, and the reason is that I selected this version for the programming is that this is the newest version from the community. The other reason is in this version, and maybe from the OpenFoam 10, we have seen many big changes in compared to the previous ones. The other reason is that there is not that much tutorials available online for OpenFoam 12 programming. Of course, although this is an OpenFoam 12 programming course, but what you have seen and learning in this lecture can be applicable to the previous versions also, and you can extend the version 11, 10, and even the before that using this tutorial with minor changes. The other reason of focusing on OpenFoam 12 is that installing the OpenFoam is relatively easy even in the previous versions, but the OpenFoam 12 installation is absolutely one of the easiest programs that you can install on your machine, which I have gone through it in my previous videos. You can check them down later. So if you haven't installed the OpenFoam 12, you can go back and watch the video that I put it on the screen right now. That's great. Now let's jump into the topic. The topic for today is for viscosity laws, which name scale viscosity power law. As you may already know, the power law of viscosity is already implemented in OpenFoam 12, which the equation looks like this tau that you can see on the screen. The tau is the shear stress, the gamma is the shear rate, K is flow consistency index, and N is flow behavior index. What we want to do at this point is to add a scaling factor into it. It's a dimensionless parameters that we want to introduce to modify the exponent part of the equation. Basically, in the power law viscosity system, if the n, the variable in the power, is greater than 1, the fluid is shear thickening, and the viscosity increases with increasing the shear rate. Some materials like suspension or cornstarch in water can be an example of this behavior type for viscosity. If the n value is less than 1, it's a shear thinning fluid or pseudoplastic, and the viscosity decreases with the increasing shear rate. Examples are like ketchup, blood, and many polymer solutions. If the n be equal to 1, then the fluid behaves as a Newtonian fluid with constant viscosity. Now, this custom power law is a model that you came up with and want to implement inside the OpenFoam 12. So let's jump to it. In OpenFoam 12, the object-oriented programming have been used, which is pretty complicated, but fortunately, this is the method that has been used in the core of OpenFoam. And if you want to develop something on top of the OpenFoam, it is not that hard to get to it and also to get used to it and expanding the already available modules. I assume that you have already installed the OpenFoam and prepare an environment for your development case. If we go to the OpenFoam 12 main folder, you have a couple of subfolders here. If you have already familiar with OpenFoam 12, so the tutorial must be a familiar folder to you, which includes all the available predefined cases for your simulation that you can modify based on your own case. But for you as a bit more advanced user that want to extend the usage of the OpenFoam, there are two other folders that are much more important. The first one is application and the other one is the SRC or source folders. Basically, in these two folders, all the underlying programming of the OpenFoam 12 and indeed the OpenFoam 12 core has been seated there. The other folders are not that much important at the moment. As I said, the core part has been set in these two folders, and mainly the source folder is the place that you can find the codes, and somehow the derived version of the source folder is sitting in the application folder. This source folder is a home to different models, such as material models, physical models, or numerical methods, even the input and output of the classes and the definition of the classes. Using these classes and the models, also the methods, you will create the applications that you will use in your own simulation. In the application, there are different solvers like the pimple foam, the foam run itself, foam multi-run, or even the legacy ones like Laplacian foam, RowPro simple foam, IcoFoam, and so on. it should be mentioned that the version 12 of the OpenFoam has been changed so much in compared to the previous versions like the OpenFoam 6 or 8. Also in the utilities, you have other tools that can be used in your simulation like post-processing or pre-processing, parallel processing, and so on. We will come back to this folder in the very last session, which we want to develop a new solver. But for today, we are not going to look into this folder, but we'll go toward to develop a material model, or indeed extend an available material model. As you have seen in the tutorial sheet, we only want to add an S factor into our already available module. So the folder that is relevant for today's lecture and also the next session is the source directory. There are too many files and subfolders here for different objectives. Frankly speaking, I don't know most of them, and even I don't think if I needed to use them. If you want to look for a file in this folder, it takes ages to do, but the solution is that open a terminal and searching for what you are looking for. For example, if you are looking for the viscosity law, you will search it by using the grep and recursive option. So you are looking for a power law viscosity model, you will search it and you find the available files with the same name. Basically, as you can see here, the command will return what power law I've found in the files and also in the text that inside the files. So it both search for the files itself and also it takes a look into the files, for example in this line, and if it finds the same word, it will return it into the terminal. So basically you are looking for the powerlaw.c and .h file under the viscosity model. So take a look into the address, momentum transport models, laminar, generalized Newtonian viscosity models, strain rate viscosity model, powerlaw.c. How we make sure we are looking for this file, because the other ones like this one, atmospheric models or the porosity model, here again the porosity model are not we are looking for. We are looking for the viscosity models that are already mentioned in the directory folder. So let's take a look into this directory, momentum transport, laminar, generalized Newtonian. Just keeping in mind that in OpenFoam, always the name of folders and files are totally meaningful. As you're going down into your address, you have the feelings that where you are looking at by the name of folders you are passing. So here when you enter the generalized Newtonian viscosity model, you go into the strain viscosity models and then the power law. You have two files here. Also, something else that you should keep in your mind is that this grep command is really sensitive to the capital or non-capital words. So it's basically case sensitive command, which is the case mostly in Ubuntu. If I use the small l, then it doesn't find anything. But if I write it down like power law with a capital L, then it returns what I'm looking for. Let me clear the terminal and do the search again. As the tutorials and using the OpenFoam, we never start from the scratch. We always look for the very similar case of tutorial folder, and then we modify it based on our needs. Basically, it's the approach that we also take in extending the OpenFoam. So I have this power law folder with a .c and .h file with which I will introduce it later, but I copy it and paste it into my working directory. .h is the header file, which is a basic knowledge in C++. The h file includes the definitions and variables, and the C file includes the main functions and constructions, classes, and other stuffs. We will take a look into them, into the details later in this session. Now let's first open the C file, the powerlaw.c and powerlaw.h. Let's first go to the h file, the header file, because I want to show you what exactly the h file includes. As you can see, the first part is a comment section. Basically, it is not the part that compiler are going to compile. It's just comments, as you can see in purple color, or maybe different color in your own systems. Let me a bit zoom in. So preferences, font and colors, and then let's increase the font size a bit into something like maybe 16 is enough. Yep, I hope it's visible now. The first part is the comment part, the h file. In the h file, we always define the class declaration in object-oriented programming. For example, the name of the class, the public members, the private data or private members, and also the constructor of the h file and the deconstructor, which is the C++ knowledge. Here, the powerlaw is the name of the class, as you see here. And also you see the private members like k, n, new mean, and new max. The underline after these names are a common programming style that shows these variables are temporary ones and show they are the private member of this class. After this public keyword includes the public members. Basically, in the header file, we define the parameters and variables that we need in our main program that includes in the C file. The source file is included in the .c file. Again, at first we have a command which says this is the part of the OpenFoam, and then what is the OpenFoam and so on. We have a static data members here, and also before that includes two different files. The first one is the powerlaw.h file, and the other file that has been included into this C file is the @runtime selection table.h. We do not touch the lines that we do not have any idea about. So basically we only touch the lines that we already knew is related to this very specific model, and only change the lines that should be changed. But we do not change the structure or the variables or the main parts of the code. The source code is the translation unit also. It's called as a translation unit. When the compiler starts to compiling, it reads the C file and then start to compiling using the C++ into a machine code. But the .h file is the interface, somehow instruct the other files. instruct the users of the code how they can use or call or even create an object in your own source code. At the same time, it also constructs the other translation units, how that source code can interface the power law object. I hope this hadn't explained the C file and .h file a bit. Of course, it's possible to add the main function into the H file, but as a manner of programming, we just try to keep the coding parts, the main coding parts, and the programming core into the .c file. We always try to keep the .h file as short as possible, just like what we have here. When you include the .h file here in the .c file, the whole file of this .h here in the .c file. Also in the .h file, after the description about the OpenFoam, it shows where it comes from, which class is it in the OpenFoam 12. And then it has some description about the power law generalized Newtonian viscosity model. It includes the formula itself and also the default value of the variables. But they are just comments. It will not be compiled through the compilation process. I will not go more into the details for this section because it's getting more and more complicated and more than what we need at the moment. But one other thing that you can see here in this header file, another header file has been included. That may be because we need something from that header files or some definition has been done there, and we want to include that very file into our own extension. Also, the OpenFoam has many namespaces. Basically, it gives you the access to different part of the functionality in OpenFoam. For example, here we have the namespace foam, which is the mother space of this program, which is OpenFoam 12, and then comes to the laminar models and the namespace generalized Newtonian viscosity models. With laminar model, we access to the laminar one, and with the third one, we will access to this generalized Newtonian viscosity. Basically, we don't need to know them very in detail. I guess that's enough for the moment. You always just follow the similarity and then extend it based on your own model. Then we define the class. Basically, we give a name to this class, which is power law here, and then we need to access to this strain rate viscosity model, which is public here, and basically this power law inheriting from a strain rate viscosity model. That means you have access to all the strain rate viscosity model gives. If you are not familiar with the inheritance, then don't mind, you just continue with the tutorial. Basically, the definition of this inheritance is the same as I gave you, but at the moment we will not go much more into the details because the C++ word, which is a very, very deep to dive at the moment. Also, we have the private member of this class, which is the kn, new min, and new max that I have already mentioned. Then we have the public members, which is the type name is the first one. This name is important because your library will introduce with the very same name into the other part of the OpenFoam. Basically, when you want to add your developed model into your simulation case, you should use the same name there and include it into your own simulation, which we'll see in this tutorial. The next part defining the constructor and destructor of the class. Basically, the part is the very first section that have been run by the solver when it comes to the power law. So, and then the destructor is a part then that has been run when the solver used this class. Basically, when it want to start to run the power law, this section will be run, and when the run has been finished, this destructor will be run. Usually you leave these parts with the default definition except this line, the type name. And then you have the member functions. They are basically the main functions that doing the job. Now we have seen enough from the header file. We can move to the C file. Going back up, this part is only about the license and its comment. We include the powerlaw.h file, the file that you have seen in the folder, and then the include add to runtime selection table.h. Basically, using this add to runtime selection table, we will access this library during the simulation if needed. It's a nice feature of the OpenFoam, but we don't have to touch it and worry about it at the moment. We have the static data members. We will not worry that much about this part. There is some changes here which we will reach to, but at the moment let's just focus on what we have here. Then we comes to the constructors. Again, the parameters and the classes that you're using here is defined here. What we need here is the viscosity properties, foam viscosity and viscosity, and then the velocity field here in this class. Also, we have the parameters that we already defined the H file, and we'll initialize them with 0 here. First, we try to initialize the strain rate viscosity model using the velocity field and the viscosity properties and viscosity. For initializing the K value, we'll use the dimension kinematic viscosity and 0. For N, it's 0, which makes the model as a Newtonian fluid. It's just the initial value. You can change it based on your need, and it's a dimensionless variable. Nu min and nu max makes the new value to be limited into a range. Right now it's 0 and 0 for the initial value. One other keywords that I want to talk about is the dimensioned scalar. This keyword shows that these values are a scalar and not a vector. For the moment, we only need the scalar values. Basically, if you want to use the constructor of this function here, you should check the file of a strain rate viscosity model and then see how you should use this constructor or function. But we choose another way, which is not touching the functions that much, just using them as they are, and then add our own formula or definition on top of the already available models. You should always try to find the closest class into your own model and then try to modify that one. This scaled power law was very close to the power law that already been defined into the system. Even for different libraries like population balance or the breakage and coalescence kernel in population balance, you can just pick a kernel like Lewis Sweden and then modify it based on your own formula. It was a bit off topic, that's what I had said, but it's something relevant. You should just keep it in mind and start with the very similar case to what you want to develop. So basically, after the initializing the variables, we will read the viscosity properties. We call the read function and then the correct function. This correct function have been already defined probably in other included classes. So that's why we do not have it in the H file, but yet we still can use it. For example, for the read function that we have already used in the C file, we already defined it in the .h file. Read function, which read transport properties dictionary, and then it returns the laminar viscosity from that very file. In the developing process, you may not always understand everything, just like what we have here, the correct function. We do not know where it comes from, we do not know what does it do, but yet we know that we shouldn't change the original file that much, because changing too much in the files requires the knowledge about the templates, about the classes inherited, and also the C++ core itself. Next thing is the member function. The first one is the read that you have seen in the header file. The parts that is much more interested part is this section. Basically here the read function tries to read the k value from the transport properties dictionary. So basically we have defined a read function here, and if we see the transport properties file in our case study, then there is a new value, and these functions try to read the new value that already defined in that file. So in this case we also read the k, n, new mean, and new max values from the coefs part of viscosity properties in transport properties file. The next part and the variables that should be calculated based on the parameters that we have already read, and this part is the main section that we are focusing at the moment, is the new, because we want to calculate the new based on the new 0 and the k value and also the n value, and then restrict it to the new mean and new max values. In that way, the new value will never goes beyond the new max and less than the new mean. The return file, the return function, or indeed the returned value will be the maximum value of the new mean and the minimum value of the new max, and the main formula that we have seen before, basically this formula, the k multiplied by gamma to the power of n minus 1 here. Basically this is the formula that we see in the .c file. K value multiplied to the strain rate to the power of n minus 1. Now we know the H and the C file. We'll start to modify them based on the scaled power law. We have already copied into the our directory and working place. Never try to modify them in their own home folder. Never do that, because it causes a big crash into your OpenFoam itself. Always copy them into your own working directory, like what I had to do here. And then first rename the folder scaled power law, and then I rename these two files to the scaled power law. I open them both again. Also, we need a make folder. What is the make folder? Basically, it is a predefined folder in OpenFoam that the developers put there for compiling the files in the folder. And by copying that make folder into your own folder, then it gives you the OpenFoam the idea that there is a folder that should be compiled in the OpenFoam. So basically it's a predefined approach for extending the OpenFoam. If you want to find the make folder, you should go up in the powerlaw folder in the OpenFoam 12 directory. So we have the powerlaw, we go a level up, we look for the make folder, there is no, again, we go another folder up, still there is no make folder, we go again upper and then upper. In the laminar flow again, there is no make folder, so we have to go another level up. Here we see the make folder, and we will copy it and paste it into our main working directory. So that's the way you can find the correct template for compiling the developed library. So one more time, wherever you are, like the powerlaw, you start to go up to find the make folder. This is the easiest way you can find the right make folder and then copy it into your own working directory. So we have the C file and .h file here. In the scale powerlaw, I will paste it here beside the .c and .h file. So let's go to the make folder. There is files and option file here. I will try to open them to take a look into them. Files and option. Basically, we include all the needed library here in this option file, and the files instruct which file should be compiled in this process. So in the files, you can see a very long list of the C files that tells the compiler to compile them. But basically, we don't need to compile all of these because they are already having compiled in the solver itself. Let me first find the powerlaw. There are two powerlaws, but one is cross powerlaw and the other one is the powerlaw. We only need this powerlaw. The only thing that I need is this line, the rest having already compiled. So I will delete them all. And also the line here. The only line that I should keep is this powerlaw.powerlaw C, and the very last line and the address of the place that I want to compile it, but with a minor difference. This $sign shows that it's the relative address of this powerlaw file, because the make file is already set into our working directory. We don't need to use the relative address, and we only use the absolute address of the file. Basically, it's the address of the C file. We already renamed the powerlaw and C file, so I will put the scaled powerlaw.c. The second line, which is the lib, we need to change it from the default directory to the user one. So I add a user here and then add a underline here. And the thing is that we want to define the library compiled version of this scale powerlaw. So we will rename this line into something like this. But the thing is that the lib should stay here in the naming. That's how it gets introduced to OpenFoam as a library in the simulation case. So I made two changes in this line. The one was adding the user underline in between, and the next one was the renaming the section to the lib scaled powerlaw. Now let's go to the option files. I saved it, and then in the option file, there is not that much you need to change him. You only need to add some lines here. The powerlaw has been already a part of bigger library. Let me show you. Here it was powerlaw, and then I went up and up and up to see the make folder, and also I can see this laminar folder that I have been already there. So basically, in the momentum transport models, you also have the ln include folder. which includes all the functions and modules that already has been compiled. So basically we need to create something similar, but to do so you need the original file and open it beside the original option files. So basically right now you have the original files opened beside the option file that you want to modify to also include this library into the compiler process. So if I scroll down in the files, I need to include this original library here. So I will just add here, and then I need this library with a minor difference. I only need the L in front of it, L momentum transport models. I have already mentioned what is exactly the LN include. It's the alias for the compiled libraries. I also need to include this folder into our modified version, so I will open it again. And in the option file, the first section should also include this library. So I will add this relative part of the address, and then I will show the properties here and copy and paste. Then I will paste this part of the address here. So basically it's the source folder, which is also again here, and then momentum transport models, and again momentum transport models, and then /ln include, which will come to this very folder again. Great. We add all the files and library we need here. Now we need to do the modification in the powerlaw and scale powerlaw.c and .h file. As you have seen, the powerlaw, the original library name, has been mentioned many times in the h and .c files. 7 times has been mentioned in this file. What I should do at this point is to replace all the powerlaw with the scaled powerlaw. So find and replace powerlaw with the scaled powerlaw. Replace all here, and I save it. Same for the h file. I replaced all the powerlaw keywords with the scaled powerlaw. So let's replace it again. Great. So it was very easy just to replace the name of new library into the old files. So just to make sure we have gone in the right way so far, I open the terminal and load the OpenFoam 12. And then I use the wclean first. It is not compulsory, but sometimes it helps when a library has been compiled falsely. So using the wmake, I try to compile our library. We didn't change much, only I rename the files and include the correct libraries. So as you can see here, lib-scaled powerlaw, the library that should be included in the case of the simulation, has been named here, and the compilation has been completed, and ln include folder has been created here. So now I want to use this library, although it's the same as previous one, the formula itself, but I want to use it inside a simulation. So I go back to the OpenFoam main folder, tutorials, and then I pick a simulation in incompressible fluids. I choose the PITS daily, for example, and paste it into my own working directory. I just go there, open a terminal, just want to make sure my OpenFoam working. Block mesh if it has, so there is no block mesh directory. I will go up into the resources and find the block mesh file there. Block mesh dict, I'll rename it, and then the mesh has been created. Then the solver is incompressible fluid. I will use the foam run instead to run it. So the case is running right now. Let me just create a copy of it and name it with the new library. So scaled power law. Now let's open it, go to the control dict and include the library that we have already developed. Just one thing to make sure about the momentum transport is rest right now. I want to use the laminar. In physical properties, I do not want to change it at the moment. And let me change it in the original Pitts daily, because I want to compare them after defining the scaled power law. So let's go to the scaled momentum transport and put laminar here also. So the simulation will be in the laminar. I try to run the Pitts daily. For a couple of moments and then start to now we want to include the compiled library into our simulation. So I go to the control dict file and then lib and semicolon at the end. The name of library that I have used here was the same as the one here, so I will copy and paste it simply. Lib scale powerlaw.so. I save it, and now I want to use it in my own laminar model. So I will stop the simulation, and yep, it has already been done. So here in my own power law folder, I use the laminar simulation. I open the momentum transport, and now I want to use the power law viscosity model. So basically let's use the same keywords here, and laminar, the model would be generalized Newtonian. The other way that you can find out how is the syntax for using this viscosity model is to search it. Let's go back to the very beginning terminal, like you have already seen how we search for a name. It's better to go a folder up and then try to take a look for the grep power law in the tutorial. Waiting a bit for finding the power law. I didn't find the keywords, so let's check, for example, the viscosity model. So the only options that it found was the constant one. So basically let's open one of the examples, cross power law, or let me see if I can find the generalized. I don't think so we can find it, but let's try it first. Yeah, there is one in the incompressible fluid offset cylinder. Let's go to the tutorial, incompressible fluid, and then offset cylinder, constant, and momentum transport. As you can see here, it used this syntax to include it into the simulation. So let me go back, and first I will clean the case to use the main power law for this simulation. So foam clean tutorial to clean the case, and then I will go to the constant momentum properties and paste this laminar dictionary here, and I use the power law. What variables do I have in this simulation is the k, n, nu min, and nu max. So k, n, nu min, and nu max. For the k, I put a very low value like 0.001. For this one, I put like this, and nu minimum is 0. A very low value. For the maximum viscosity, I placed something like this. So I saved the simulation, and let's run it again. Clear for the terminal, and then block mesh, and then foam run. Let me take a backup for the later and name it its daily scaled power law. The simulation is ongoing. It's slow but yet okay-ish. Now in the scaled power law, I want to include the library that I've already mentioned. So, and now I should be able to use this scaled power law here in this simulation. Just make sure you have this lib keyword here and include the compiled library also. Here now I want to run it, load the OpenFoam 12, and then block mesh just to make sure, and foam run. I want to show you something first. Here what has been selected is yet power law. So if we want to use the scaled power law, we should change. It was already open in the text editor. I reopen it. So here we have the power law. I want to use the scaled power law. So let's resimulate it again, and then a very nice error you can see here. It's basically the banana approach. As you can see, the name of the scaled power law cannot be seen in the list. So what we should do at this point, so we have already included the power law here, but something that I forget to put, it is not lib keyword, it libs. I save the file to control it, and let's again foam run here. As you can see, the Newtonian model right now called a scaled power law. So now the simulation using the library that we have already developed to some extent, it's time to go back to the .c and .h file to modify the formula. To implement the scaled power law, first we need a s variable. So I use this s factor here. Also, for the future reference, you can add a scaled factor in the description and put, for example, a initial value or default value for this variable. So far we have added the s in the h file, and the underline show it is a private member. If you continue to scroll down, there is no places need to be changed. The reason that I used the n dimensioned scalar and copied and pasted again to change it to s is that in the formula, the n and s should have the same characteristics. So in the C file, you can see it much more clear if I copy and paste this line again and change it to s, because the n is dimensionless, the s should be also a dimensionless variable. Now we need to change the s part for here also, so I copy and paste it and put the s underline should be read from the transport coefficient. So to add the scale power law here and including the formula, we go back here. As you see, n minus 1 over the s has been added into the new formula. So we go back to the .c file, and this part should be divided by the s factor. So I put them into the parentheses, one more parenthesis, and then divided by s factor. Similar to the way that the n variable used, we directly use the same syntax. So basically n value minus 1 over the s underline dot value. Now we go back to recompile it. We already simulated this pits daily, so I don't need this terminal, and also don't need this one. I need this, so I use first wclean to clean the previous version, and then wmake and wait for the compilation to see if there's any error. There wasn't any, so I go back to the custom simulation. As you can see, we are in the pits daily scaled power law folder, so I block mesh just to make sure, and then foam run. There's a nice error here again. The keyboard S is not defined in the momentum transport file. So right now we know everything is working. There is just a small thing need to be changed, and I should add the S value here also. I use the value like 2 and save it, and again I try to use the foam run. Still there is no S defined here. Yeah, that's true. I should rename the N to S, save it again, and to just make sure everything is clear, we again use the foam run, and it's running. In the first simulation, I try to open the power view. So let's see if it can be started here. It's the pits daily.openfoam. It's the original simulation of the power law. I use the U because the viscosity directly affects the velocity field. Okay, and now let me open the other version. Yes, it's simulating. Just create a .foam. For the power view, and then go back here, pits daily, all files, and open this file, which is an OpenFoam type. So let me open another section over here and zoom it a bit in, go back to the initial condition. As you can see, the initial condition for the velocity is the same. I don't want to skip to 0. I don't know if it can be used here. Yeah, The initial condition right now is the same. I want to use a 2D format of this and then zoom a bit in. The simulation has been already done, so need a bit more zoom in. Now if we start the simulation for 0.05, the system that I'm using currently is a bit low end. That's why I keep receiving this notification message. As you can see, the changes is very significant. It can be visible here. Let's go to the very last time step. I will also put the simulation video. Now I have exported the simulation as a video file. As you can see, the developed model works very smoothly. And now it was the last part of this tutorial session. I will upload the simulation file and also the modified versions on my own weblog, so you can download it and use it as you like. In the next session, we will go through developing a custom boundary condition, and I will meet you there. Thank you for watching and have a nice day ahead.